Hey, welcome to today's lesson. You'll notice that I'm doing a different format today where you get to kind of watch me in action and see how we do things. So today we're gonna see if we can graph generic functions. And these are functions that aren't defined algebraically through an equation. These are functions that have already been defined graphically. So the first function, called g of x, is this just weird graph that's just zooming along like that. And what I want to do is I want to see if we can apply our understanding of functions and parent functions to manipulate these functions. So g of x, whatever it is, and I don't know how it's expressed algebraically, although my guess would be is it would be a piecewise function, but this is what g of x looks like. And the very first thing I want to do right here is I want to graph what g of x plus 2 plus 3 looks like. And this one you might just be able to do logically. I mean, after all, you know that this plus 3 is going to move all my points up 3. And you probably have already figured out that this plus 2 being inside the function is going to move all my x's to the left 2. So this one, what you could do is you could just grab a point like this point right here, and you could say, okay, that point, which is at -1, -3, which is right here, is going to move left 2, but up 3, and end up right here. And then this point right here, which is at the origin, would move left 2 and up 3, and that would put it here. And so since this is nothing more than just a shift, you could just take this graph and you could just shift it. Every point, 1, 2, 3, 4, is going to move left 2 and up 3, every single point. Now, let's see, this line here seems to have a slope. We go, rise is 1, the run is 1, 2, 3, 4. So 1, 1, 2, 3, 4, right there. So we can just do a little shift, and it really doesn't seem like this is that difficult. And so, you might get all cocky and say, oh, yeah, look, this is super easy. And then all of a sudden, we come down here to number 2. And number 2, we're not shifting this graph, but we're scaling it. And now you might get, a little panicky and say, oh my sweet mother, what am I going to do with this? Well, lucky for you, you happen to have one of the most foolproof, brilliant techniques for graphing out there. And that technique is known as the Birath Technique, named after one of the premier mathematicians in the world. And this technique, the Birath Technique, we already know how to handle it. I mean, how do you handle the Birath Technique? Well, the first thing you do is you find the new origin. And so if I look at this graph right here, 2g to the x, it looks like there's no horizontal shift, there's no vertical shift, so it's going to just stay at 0, 0. And so what I'm going to do is very likely, I'm going to just put a little mark here, and the new origin is really staying at 0, 0. Well, the second thing you do in the Birath technique is you look at the parent function. And the parent function in this case is g of x. And you make an xy table. And that xy table is a table of movements from the origin. So the first point I notice up here is left 1, down 3. So the first point is -1, -3. The second point I care about is 0, 0. The third point I care about is 4, 0. And the fourth point seems to be right there, and that is 5, 6, 7, 8, 1. So whereas in the graphs we've been doing that have been defined algebraically, we found these movements algebraically, since this graph was defined graphically, we find these movements from the graph. Now, when I look at this problem here, I see that I have a scalar out in front of 2. And that, of course, affects the y's. So all I'm going to do is I'm going to double my y's. -6, 0, 0, 2. And now I can plot these, what are they? They're movements from the origin. So from the origin, I'm going to go left 1, down 6. From the origin, I'm going to go over 0, up 0. From the origin, I'm going to move right 4, up 0. And from the origin, I'm going to move right 8, 6, 7, 8, up 2. And when I sketch in my graph, now remember, this graph does take a turn going horizontally. You'll notice that this 2 out in front stretched this graph up here, sketched this graph, stretched it vertically. Didn't stretch it out horizontally, stretched it vertically. So this Birath technique that we learned for algebraic, or for functions defined algebraically, it works for everything. I mean, that's the versatility of the Birath technique. Really, really an incredibly high functioning graph. Now let's do number 3. So number 3, again, using the Birath technique, we know our new origin is still 0, 0. That hasn't changed. There's no shifting going on here. And when we define g of x in terms of its movements, we know that we have the same points. -1, oh, I'm sorry, I'm going off the page. -1, -3, 0, 0, 4, 0, 8, 1. And again, we're not using our starting lineup of -2, -1, 0, 1, 2, because it just doesn't make sense here. I mean, the points that I care about are these significant corners of where the graph is changing. So now I take a look in here and I say, well, golly, this 2 is going to affect the x's because it's inside the function. What's it going to do to those x's? It's going to multiply those x's by half. It's always the opposite when you're inside. And so this becomes -1/2, 0, 2, 4. And so what I can do, let me grab a pen that's really going to show up. What I'm going to do is from the new origin, I'm going to move left 1/2, down 3. Over 0, up 0. Right 2, up 0. Right 4, up 1. And when I sketch this graph, you'll notice that what this 2 inside the function did is it squeezed the graph. It compressed the graph. And we talked about this in class. It really didn't compress my function g of x. What it really did is it stretched the background. And when your background gets bigger, you tend to look smaller. So we can even go over here to number 4 and look at that leads to number 4. Heaven's sakes, we can handle that. I mean, after all, the first thing we do is we find the new origin. And the new origin, let's see, it looks like we're going to take this 1/2 x plus 2, and we're going to set it equal to 0. So 1/2 x equals -2, x equals -4. So my new origin is at -4, comma, 1. And of course that 1 comes from right there. So very likely at -4, 1, 2, 3, 4, 1, very likely I put a point, because that's going to be the new point from which I start all of my movements. And then number 2, we take the original function g of x. We use the important points from g of x, which in this case we've identified 3 times now as these points. And then we scale them appropriately. And by that, I mean it looks like we're going to multiply our y's by 3. So we have -9, 0, 0, 3. And then we're going to multiply our x's in this case by, be careful, by a 2. And so this is -2, 0, 8, 16. Wow, that didn't feel out there. And so now we can go ahead and sketch this graph. from the new origin, I'm going to move left 2, down 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm going to move over 0, up 0. I'm going to move right 8. 1, 2, 3, 4, 5, 6, 7, 8, up 0. And I'm going to move right 16, up 3, which is somewhere out there. And then when I draw in g of x, we see that it was stretched horizontally. That's what that one half did. And it was stretched vertically after we shifted it. So that's basically how we can use this Birath technique to graph anything. I mean, it is such a versatile technique. Now, when you go to page 2, we have a new function. I've defined g of x differently now. Get a new sheet of paper out. G of x is now defined by this guy. So when I go to do a problem, and let's just do problem number 8. Problem number 8, we'll skip the other ones. We'll just do 8. The graph technique says the very first thing you want to do is find the new origin. And that new origin we're going to find by setting whatever's inside the function, 1/2 x minus 1, equal to 0, and solving for x. So it's 2, 1. And so what I'm going to do is I'm going to take my pencil here, and I'm going to mark very lightly the point over 2, up 1. And then the second thing we do is we say, well, let's look at the parent function, g of x, and let's look at its movements from the origin. So I'm going to come back up here, and I'm going to pick some significant points. That seems significant to me, and that's the point -7, -2. Slide this up so you can see it. And then this is a significant point, and that's -5, 2. It looks like the peak of this little bump is important, and that's 1, 2, -3, 4. This seems significant. -1, 2. This seems significant. 3, 2. Oh heavens, look at all these points we have to look at. This seems significant. 4, 0. And then this graph seems to shoot out. That's important. 6, 1. And then where else do we have a nice clean? Let's see here. It looks like that's significant. And that seems to be 6, 7, 8, 5. And I think that's pretty good. So to graph this monster, we have a lot in our starting lineup. We had to bring in the big guns. So coming down here to graph this function, it looks like what I'm going to end up doing is I'm going to have to end up multiplying all my y values by 1/2. So -1, 1, 2, 1, 1, 0, 1/2, 5 halves. Oh, and by the way, notice I didn't include the original origin here. I'm going to multiply all my x's by 2. So -14, -10, -6, -2, 6, 8, 12, 16. And then from this new origin, I'm going to have to do all these movements. Now, I'm out of time that this program lets me graph this, but I think that that's probably enough for you to see how this works. Again, the Birath technique, I'm tearing up here just because of its massive beauty, how it handles anything. But you'll notice that this function did not go through the origin, so I didn't include the origin in the parent movements. So you would, of course, end up finishing this. Tonight's homework is in Google Classroom. You can print it out if you want nice, pretty, clean graphs, or you can, again, just sketch out your x and your y axes. This homework I am going to collect, so I do ask that you turn it in before our next meeting. Just take a picture of the homework, not the notes, but the homework. Turn it in before our next meeting. Good luck. I'll see you later.